In previous class, we discussed about the key concept, the word, terminology of the factory physics. The reason we like to use the word physics because it's the very basic of the factory dynamics. Okay? So there could be many people who are not agreeing with me, but the physics of production and we are engineers in ocean systems and field, and we are familiar with these physics, mechanics. And what's the first law of mechanics? What is it? In Newtonian mechanics, in analyzing the system or motion of the bodies, what is the first thing? Mass. Yes. Mass of what? What property of mass? Mass is true. It's correct. But applying some physical law to analyze the system dynamics, something of mass. Mass is conserved, right? Same thing holds here. Conservation of mass. Okay? Factory production also should best satisfy this one. Okay? So in order to discuss this conservation of mass, let's first discuss about many parameters. First one is long run average, or in short, LRA, long run average utilization. The unit of utilization is %, and lambda, also long run average demand rate. Okay, it is a rate. So what would be the unit? Demand divided by something, right? What is the demand in terms of factory production? Number of part, number of product, right? So it's a number of units per some time. Time could be a day, a week, hour, month, some given some unit time, and somebody call this one as, in one word, throughput. Okay, the volume of product, number of units flowing in your production system. Okay. Yes, long run average capacity. Okay. What would be the unit of this capacity? Okay. Same as the above. Right. Why? Yeah, right. Okay, we are dealing with the manufacturing system. So capacity should be considered with respect to the throughput. So think about this one. What would be the capacity and what would be the throughput? And what's the meaning of those two ratio? Okay, that's the first thing to consider. Okay, based on this concept, we can tell that long run average utilization is long run average demand rate divided by long run average capacity. Think about our factory. Capacity is, for example, 100 products per month. But current throughput is 80 products per month. Then the utilization of our factory is 80 over 100, 80%. Okay? Any question? Yeah, very straightforward. Okay, and average cycle time is, refresh your mind, and what is the definition of the cycle time? Anyone? What is the cycle time?
The time taken by a certain product to finish your product.
Yep. Think of this unit. Okay. What do you think this average cycle time is then? Is 1 over. Does it make sense? Yep. That's a cycle time. Okay. Let me ask you two questions. I once stressed that the build time is different from cycle time. How this build time is different from cycle time? What's the difference? What's the definition of build time? Basically, it's a time required to manufacture a one product. Okay, then what is the cycle time then? Isn't it a time required to make a one product?
I think cycle time means about the finished product of and what
Let me ask a question. Is it always different? Cycle time is always different from build time?
No.
When is same?
For just in time, if we use just in time inventory.
Not exactly. Yep. If your throughput is just 1, then your build time is cycle time. Okay? Let me explain in this way. This is your factory. Your factory has some kind of conveyor line. Let's say this is an automobile. Okay? Car after car after car after car after. Okay? So in Hyundai Motor Company, the sonata comes out in every 3 minutes. This is the cycle time, which does not mean that the build time is 3 minutes. Build time could be 2 weeks or a month or so, okay? But when this Hyundai Motor Company manufacture only one product, then, yeah, okay? Really important, if you get confused about the build time versus cycle time, then you will get lost, okay? Let me ask a second question. Well, you know the utilization, you know the demand rate, you know the capacity, but in front of every word, I put long run average. Why this long run average important? Why? Why we have to put this long run average? Okay, since you guys are silent, you can also answer my question over there. Okay, long run average is average over a long period of time, right? Why this is important? Okay, what would be the opposite meaning of this long run average? Instantaneous utilization, instantaneous demand rate, instantaneous capacity, right? How do you compare this instantaneous something versus long run average?
Long run average means constant work, but instantaneous work is at time, I think.
Okay, yeah, you are halfway there. Okay, first thing first. We are dealing with conservation of mass. Okay, so we are dealing with the system. Think of the conservation of mass in conventional physics, mechanics. When something is go into the system and something go out of the system, these two mass should be conserved. Okay? If we only focus on instantaneous moment, the part cannot go in. Well, we don't have enough time to count the what's going in are actually same as what's going out. We need some time to actually see the throughput of this whole system. But anyway, instantaneous utilization, well, nobody tells about or nobody's interested about this instantaneous utilization at time delta t or something. It's a kind of basically utilization, demand rate, and capacity is concept is based on some kind of long run average thing. So for the convenient purpose, I will not use long run average anymore. I will omit this LRA from now on, but the meaning is still there. Okay, when I say utilization, it's actually long run average utilization. Okay? Okay. One more thing to comment is the demand rate. Okay? It is our natural thinking that if this is our system, demand means there are some customer wanting something. So if we give give something out of our system to that customer, we call this a demand, right? What is that then? If we consider our small box as a workstation, we usually call this arrival, because part arrived to our workstation and our customer is demanding our output. The next workstation is our customer. I'm the customer of my previous workstation. Okay, customer and customer server. Okay, in long run average sense, its arrival rate is same as demand rate. Mass should be conserved, by the way. Yeah, what's going in should be go out. So you may think of something. Oh well, what if we cut some plate and make two parts out of one input? So what if our system is look like that? Is it still the same? Yeah, of course. We are not equating this one with only this one. You're equating all the input with all the output, right? In that sense, it is same, and vice versa. If this is the assembly workstation, mass should be conserved as well. Okay. Okay, let's deal with some real example then. Let's assume there are several workstations like that. And by the production plan, the part should flow like this. Okay? And each workstation has some capacity like this: 150, 40, 100, 25, 100, 20, 200. Okay? I said capacity, so number of long run average capacity, long run number of unit per time. So I haven't specified the time unit, but it could be a month or year or something. Okay? And let's assume that a part is coming in 100 unit per hour. Oh, then it is more appropriate for the example that this 150 is the number of unit per time. Okay? And there is some other rules that 30% of output goes into here and 70% go to here. And 40%, 60%. Okay? How about that? Because there is only one single line, 100%. Okay. Then, is it okay here? Since the capacity is the 150, but demand throughput is 100, so it is okay because throughput is less than the capacity. Okay, out of 100, 70% come to here, which means 70 units comes here and 30 units comes here. Okay? out of 30, okay, here first, 70 goes to there, so 70. Out of 30, 40% comes to here, and the number is 12, I guess. 18, right? And 18 comes also here, and if you sums up these two numbers, 82. Okay. Okay. And if you sum this up to 100, will come out. Okay. What would be the utilization here? Yes, 50%. Simple. 100 over, demand rate is same as arrival rate, conservation of mass. The rule I utilize is that what goes in should be go out. So 100 goes in, 100 should be come out. Okay, 50%. Well, hard to calculate because what? 90%? How about this? 82%. 72%. 75%. 70%. 66. Okay, that's the utilization, and these are the demand rate or arrival rate, and these are the capacity. Utilizing only these two equations, we can analyze factory already. Okay. By the way, long run average, by specifying long run average characteristic of this system, we only focus on the steady state production system. We are now ignoring the dynamics. Okay, it's just steady state, and I guess everybody's familiar with what the steady and dynamic means, right? Okay, question? Okay, let's go a little bit more deeper into the basics. Let's assume large L is number of units waiting for a process. And large W is average waiting time for job arriving in time. Oh, sorry, in line. Okay, we are familiar with waiting experiences. When you go to the bank, when you go to Burger King, or when you go to restaurant, you are supposed to wait. So this is what we call machine or server, and there could be buffer or queue, and customers are arriving randomly, and server are processing the customer, right? We know what this system is about, and we had a variety of experiences about this kind of system. Okay. L means number of units waiting for a process, which means the number of people in the line, or length of the line, which is L. Average waiting time means how much do you have to wait to be served in this line. And this is really, really important in terms of the customer satisfaction. And what is this WIP? We talked this about in previous class. Work in process, inventory. And this is okay, straightforward. At this current moment, if inside of this line there is a L number of unit, then work in process is L. In the specific bank line, if 10 people are waiting to be served, then work in process WIP is 10. Okay? And it has a little relationship with this average waiting time. Like this. Lambda is demand rate, throughput, arrival rate, or okay, and W is average waiting time. Or we can do the simple math to say that W is equal to L over lambda. And this way it is more easier. It is easier to understand. Think of that. This specific machine capable of process one customer per minute. For example, one customer per minute. Then lambda should be 1, or 1 is too simple. For example, let's say this machine can process 2 customers per minute. Okay, lambda is 2, and the time unit is minute right now. And now let's assume there are 12 customers waiting in the line. Then 12 divided by 2, 6. So we can assume that the average waiting time would be 6 minutes. Okay? L is the unit of that is the number of unit. Number of unit divided by number of unit per time. So W is time. Okay? Any question? Straightforward. This is also the role of the conservation, and in this production engineering field, this is really, really famous and called Little's law. Okay, question? So let's think about some example. There is an assembly line, and average demand rate is about 40 units per hour. And let's assume there are 20 units waiting in the line. Okay? Then what is the average waiting time per unit? Anyone? It's too simple. This is L. This is lambda. Waiting time W. What? 102. Yeah. 102. Half hour. Because time unit is hour. Okay. What is the average cycle time then? Unit is hour? No. 1/40 hour. Right? And you know, this a little slow, and this is the very basic in production engineering. You have to kind of memorize everything. It's like when you ask multiplication to elementary school boy, what's the 2 times 3? Then 6 should be the, come out right after the question. So same thing. If I ask this kind of thing, you just have to answer it. That's the very basic. Okay. If L is 2 and lambda is same, okay? And what is W?
Is it L is 20 units waiting?
Yeah. For now, 2 units are waiting. And what is and lambda is same. What is the W? What?
1 of 20.
1 of 20? One minute?
1/20 hours.
1/20 hour? Okay. And in terms of minutes? Yep. Okay. So are you familiar with, should we get familiar with all of this? Okay. I think this, in my calculation, this W should be 6 minutes. But your sensors are a little bit different than mine. Okay. L is 2. Lambda is same. How many units per minute in that sense? Two over 3? Why? Because yeah. Yeah. Right. And W is L over lambda. L is 2, 2 over 3. Oh, it should be 3. Sorry, right? Question? Okay. Let's do the another example.
Is the working process actually for the workstation or for the whole factory?
Very good question. It could be both. If you're dealing with what's the working process in our factory, then it's about the whole system. And if you ask a question like what's the working process for our workstation, then it is for the workstation. But summation of all the working process in every workstation is the total working process.
So when we are actually calculating working process, we'll be considering only the workstations or the total factory?
It depends. It actually depends. You know, there are many levels of management, and for somebody are only concerned about what's the working process in Korea, because it's if the company is the multinational company, then there must be some national manager, and this guy's only concerned about but if you're the factory manager and if you're the workstation manager, it's up to the level of detail. Okay?
If we have beginning working process on the previous month, will it actually alter all the equations of available time?
What?
Sorry.
Sorry.
Process from the previous month.
Working process in previous.
Previous month taken for this month.
Okay.
Then will something change from the?
No. At this stage, we are just considering the system is steady, so everything should be same. Okay. Yep. Okay. Okay. A little more complicated example is like that. There is a process lane like this. It could be everywhere in many industry, and each of the workstation have its own duration. Okay, in hours. So first 0.3 hours, 0.2 hours, 0.4 hours, 0.1 hours, 0.5 hours, 0.3 hours, 0.3 hours, 0.2 hours, 0.2 hours, 0.1 hours. So it's a series of workstations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 workstations, and each workstation has its own duration, time required to process a product. Okay? Could be possible in many situations. Okay. Everything is given in hours. Okay? Okay, now you are not the manager of this specific workstation. Now you assume that you're manager of this production line, a huge part of a factory. And let's assume you want to a production rate of minimum 2 units per hour. Okay? Out of your system. First of all, the very basic question is it physically possible? And we are going to analyze this. Okay? So, first one is, what is the maximum cycle time among this? And what is the maximum cycle time allowed to make this possible? Okay, first thing first. What is the maximum cycle time allowed to make at least 2 units per hour? Think, yep. I mean, cycle time, not the build time, cycle time. So I intentionally didn't translate this wording into that wording. Okay? This whole example is to, exercise your brain. This is what you're going to confront in the factory floor. Okay? Nobody asks you about if our long-run average utilization is something and our long-run average demand rate is something. What is our something? They do not ask a question like this. They ask a question like this. Okay? You are the manager of the production line. Each have those kind of time duration. Okay? And you have to make a production rate at least 2 units per hour. Okay? Then it's your job to analyze. Is this physically possible? Okay, that's the question I'm asking to you. So in order to answer that, have to first think about this. What's the maximum cycle time allowed to make this possible? Okay, what is this in terms of that? It's a lambda. Because out of your system, it's a demand rate, right? Your customer demand at least 2 units per hour, so it's a demand rate, lambda. Okay? Okay, cycle time. Conceptually, cycle time is reciprocal of this lambda. It's right? In order to satisfy that, maximum cycle time allowed is half hour. Okay? In order to make this possible, you have to produce a thing in 30 minutes, no matter what. If you exceed this cycle time, then you cannot make this. Think very carefully. This is the minimum required lambda. And you take the reciprocal value, so minimum now changes to maximum, right? So it's a maximum cycle allowed. Okay? If it's a cycle time is longer than this, you cannot make a 2 units per hour. Okay? Okay. Based on that, do you think it is possible to make this 2 units per hour? It's a duration of each workstations. What is the maximum? 0.5. Here. right? Is it same or greater than or less than the maximum cycle allowed? Well, it's the same. So we can make 2 units per hour. Okay, I said it is duration required to make a thing, which is this is the cycle time of each workstation, right? Okay, think of it like it. Any questions so far? Okay. So it is physically possible to make a 2 units per hour, and this is your workstation cycle time. And can you calculate the utilization of each of the workstation? This is, in another word, throughput, right? And utilization is what? Can you calculate the utilization of each workstation? This is the maximum cycle time allowed. So that one should be busy. No time to rest, right? If this thing goes wrong, then you cannot make these 2 things. But for example, the previous one, you only supposed to make utilize 0.1 out of 0.5 to make this possible, right? So this one has 100% utilization, but however, this one has only 20% of utilization. Okay? You get the idea? Okay. Okay. Let me ask a question then. If you're the manager of this production line, and if you like to increase this production rate to 3 units per hour, what would you do? Same thing. Now lambda is 3. 1 over lambda is 1 over 3. It's a 0.333, right? If the cycle time is greater than this value, it is physically impossible. So identify that. This one, yeah. And you have to identify that specific workstation and have to do something. What? I don't know, maybe you can put another one, or if you're good enough, you can reinvent the process and make more short cycle time workstation. That is possible, or you can just put one more thing, and eventually this cycle time could be divided by half, right? Because there are 2. Same thing here, okay? And we are going to deal with this kind of thing in later part of the class, okay? what is the, okay, to make a problem more simple, there are 52 weeks per year, right? And let's assume the Hyundai Heavy Industry producing 52 ships per year. What is the cycle time? One ship per week. That's the cycle time. A week, right? Which does not mean they make one ship in a week. They requires about 12 or 18 months to build a ship. That's the build time. Okay, so think of it like that. You need this much amount of time to make a ship, but think of the time like this. Okay, each of ship requires 18 months to build, 18 months, 18 months, 18 months, 18 months to build. But cycle time could be a week. This is build time. As I mentioned before, if your shipyard is totally empty and you're producing just one ship, which is like this, okay, from the start, the build time is same, 18 months. What's the cycle time then? 18 months, okay? Think of a stamping station. Consists of one big stamping machine. It stamps out the automobile door panel. Boom, choo, boom, choo. Cycle time could be 10 seconds maybe. Okay? Right? What's the build time then? Same. If you're considering only for that door panel, right? Right? If you're focused on the door panel, the cycle time of that stamping workstation is actually the build time. Okay, think of that. You need to make actually you need four, to be more precise, you need 5 door panel, hatch door or something like that. But anyway, make this just, let's assume that you need only one door panel to make one car. Okay? If you're focusing on the car as a product line, okay, then your stamping station's build time is not the build time of the car. It's a part of that build time, right? So if you summarize this part of the build time to calculate the build time of the final product. But however, your final product's cycle time, the automobile's cycle time, are heavily related to the cycle time of each part. Okay, one other example. Let's say automobile is produced by 3. Stamping, welding, painting, assembly. Okay? Let's say this cycle time is 10 seconds. For paint, well, you need one hour to paint and dry. Assembly, I don't know, maybe 30 minutes. Okay? I said for stamp one part, it requires 10 seconds. So, cycle time of the stamping machine is 10 seconds. And build time, if you only consider this stamped part, the build time is 10 seconds. Okay? How about this? How about this? It depends on the product and processes. Okay? If this is the cycle time, then there is no way to produce a car in every 10 seconds because it requires an hour. For example, applying a painting and let them wait for it to dry, you requires kind of 1 hour or so, right? So 1 hour is more like a build time for that painted part. But in many automobile assembly plant, what they do is they use conveyor line. Cars are waiting here, and at some stages, robotic arm applies the paint, and every car is just go and go and go, and while moving, it is dried, right? So, even though the build time is 1 hour, the cycle time could be much less than that in this kind of workstation. For the one single stamping machine, build time could be a cycle time, but could be different build time and cycle time even for some workstation. You know, it's all about the level of detail you are interested in. Okay? Painting workstation could be subdivided into many sub-workstations, cells, and the like. Okay? In Shipyard, panel line could be a workstation. Okay? Cutting station is sub-workstation, belongs to the panel line, and the like. So have to be very careful identifying, is this actually build time or is this actually cycle time? Concept is really, really simple, but in the process of application, you have to think very wisely. And applying this little slow and conservation of mass of the product factory physics, if you're confused about build time and cycle time, everything will be messed up. Okay. Okay. I'd like to introduce something called Polasek Kinchin formula. Let's say L is the average number of units waiting for a process. In another word, this is a queue, in the queue or working process, WIP. let's say K is some constant. Let's say V is some measure of product or process variability. Okay? And they proposed this model. How? It is the result of their research paper. So deriving this equation and justifying why this equation holds is beyond the scope of these courses, but think of that. K is some constant. Okay? What is this? Rho. Utilization, right? Percent. So utilization over 1 minus utilization. So it will be cancelled out. So the unit is scalar, non-dimensional number, and some variability. Very important. So it means this. Let's assume this x-axis is the utilization. Okay. Y-axis is the working process, or L, the number of units waiting in the line. This is about this asymptotic line means 100% utilization. Okay, this formula explains the effect of variability in your factory physics. Okay, based on this, can you guess out of this V3, V2, V1, what is the largest number? You know, there is a clear tendency, so you have only two choices, V3, V2, V1, or vice versa. Which one is correct? You can put any number, so take a 50% utilization. 50 divided by 50, so it will cancel out, and you can compare this value. So why? So K times this part now become constant, so V3 is the highest, L highest, so this is true, number one, right? Any question here? So mathematically, it is easy to identify the different variability affect the shape of this chart. And let me ask a question. How do you interpret this chart? So what this chart mean?
As we increase the working process, actually we are going for the 100% utilization.
And in another word, Yeah, okay. First of all, in utilization axis, is higher utilization good? Is lower utilization good? Higher is better, right? Everyone wants 100% utilization, right? If you're achieving 20% utilization, then it is waste of money. You purchased too good machine for your production system. So 100% is best. How about this y-axis? Is larger working process good? Working process, in another word, L. And I explained that L is the number of people waiting in front of the bank, in front of the Burger King. Is long line good? If you're a business owner, then it could be a good thing, but usually it is not. Assume that the server is the machine and customer is the part waiting for to be processed. Is L, larger L, bad. Smaller L, good. Zero L, ideal. Okay? So, what we want to achieve is this area. Lower L, higher utilization. But if the V value is higher, we cannot go there. Okay? If the variability is really low, if the V1 goes to 0, to the extreme value, it will go like this, right? Okay? Even though you're increasing the utilization, your L does not affect it at all. But really low variability is not possible in real world. So there might be some, the worker, the people working on Monday and Wednesday is different people working on Tuesday and Thursday, and these things are happening. And if this guy are sometimes, if today is this guy's birthday, and if this guy is really happy, then the production rate affected. Okay, there is a little variability even though we are producing identical thing. So low variability, it is easier to achieve higher utilization without increasing L. But if you have the high level of variability, then we cannot go there. If you're trying to increase the utilization here, then L increases. Okay? That's their formula. So based on this model, is higher variability good or higher variability bad? It's not good. We want to stay this area, but we cannot go there if the V has higher value. So higher variability is bad, and we want to avoid it. Okay? But in ocean systems, in shipbuilding process, we cannot, because product is unique. Inherently, we have variability in product. Okay? Okay, one more thing. The key idea of the group technology is gathering the similarity out of unique product to make an effect of economies of scale. So even though we gather a sum part with higher similarity between them, higher similarity means it's not identical. It has variability. You cannot achieve lowest possible variability level. This variability comes from the different design of product, also from many other places. And can you guess what would be the typical source of variation in factory? What is what is the most common variability? What do you think? Yeah, of course. That's the first thing. Think of that. If you are the manager of Burger King out there, the demand is not uniform. For example, in today, there are 100 customers. So tomorrow, will that be 100 customers? No, it will be variable. And in order to reduce the variability, they try to forecast the demand. The reason is that if the variability does not affect the production system at all, what's the good of forecasting? Okay? If they can forecast very exactly, then you can think of it and reduce the variability. Okay? And what else? For larger level, customer demand is only for the final product. But if we go inside of the system, I'm the customer of my previous workstation, and my next workstation is my customer. Okay. Within the system, we don't know. I think it's a kind of stupid to say, but in real yard, you don't have enough idea how much throughput my customer wants in a week later or a month later. So, same thing applies. They try to forecast it, but everything is inside of our factory or shipyard. Forecasting demand between the workstation is, in another word, planning and scheduling. So they put lots of effort to make a very precise plan and scheduling. Okay? Or, nowadays everything is related to the information technology. So they try many other things. If you instantly know the exact demand inside of your yard or factory, it helps you in a way to reduce the variability. So that's the major reason people try to implement information technology. Like by pushing a button, you know all the information you need. That's the one thing that reduces the variability. Another word is randomness. Reduce the randomness. Okay? The other thing we do like to see is the reduce the intermediate product variability. That is also greatly affect the reducing the variability. That's why many factories are You know what this means? Trying to make things a standard. They do that to reduce the product variability. Also, they do process standardization to reduce the process variability as well. Okay. So, we just talked about this variability affect the L, work in process. Okay, and we agreed that larger work in process is bad. And why do you think work in process is bad? Why? Work in process, in another word, is inventory. Why this is bad?
It is triggered to reduce one product and might may lose its customer.
Yep, true. And for factory level, there is a part sitting, just waiting to be processed. It's an inventory. If you have the huge inventory, is it bad? Why? Because?
The cost
Exactly. This huge inventory, unfinished part, is money, right? Money is sitting there doing nothing, which is bad. If you put those kind of money to the bank, you earn interest. But if the money is sitting there doing nothing, then it's just waste of money to that interest amount. And one more thing is that it takes spaces. So waste of space as well. And second thing is, something is happening to this intermediate product. It can be ruined, damaged, rust, things happening, right? It can be broken. It's also a waste of money, right? And the other thing is, okay, let me ask you like this. Everybody understands that inventory is bad, but why people make inventory? Everybody knows that this is bad, but everybody are making inventory. Why?
And forecast the funding for customer.
Yep, you got the point. Because of variability. If something happens, they do not want to starve my customer. So, in my workstation, something could happen. Machine can be broke down and the worker will not be available. Something happened. But if we have lots of inventory, we can use it during we are fixing the machine or and the like. If there is a many variability, so we need a frequent change of tools and other setup time. But during that setup time, we can still feed our customer because we have inventory. Okay? But inventory is bad. Okay? It's like fat around your belly. It is bad, but it helps when you starve. You will not die because you have some energy stored around here, right? But eventually it's bad, right? Okay. In today's class, we just briefly discussed about the very basic of factory physics. Everything is based on this rule. And with this tool, you can easily design a simple factory based on the utilization, throughput, and capacity. And based on this, people actually designing a factory. You know, they have planned. We'd like to make this much amount of this product. And there is some machine with capacity of this one. And there is in order to make this much of the product, throughput should be like that. Then you can assign, workstation and routings and everything. This is called capacity planning in a basic level. So with this knowledge, you can actually design a very simple factory. But that's not all. Since this basic law, we assume that everything is steady, but there are variability, and have to think about the variability because it affects everything. And dynamic nature of this thing could be also another variability. So we talked about basic law, variability, and based on this, in the next class, we think about the optimal level of inventory. We'd like to reduce the inventory. There must be some optimal level, and there is many formula to determine this optimal level of inventory. And we will continue on this factory physics. Thank you.